Before we start, let me just talk about the gamma 5 puzzle that I posed a few lectures ago. And the question was, what would happen in 5D? What would happen to the representation of 5D? And so here's the answer. So this is the Dirac equation in 5D. So here, does the indices go from 0 to 4? So in 5D, you have 5 Dirac matrices. But notice that the matrix you call gamma 5 in 4 dimensions, if you just relabel that matrix to be gamma 4, then these 5 matrices satisfy the Dirac algebra in 5 dimensions. So we can actually reuse the 4x4 matrices that we found in 4 dimensions from 0 to 3, and then relabel gamma 5 as gamma 4, and then we have a Dirac algebra in 5 dimensions. So you might say, okay, that's all fair and good. Can we have Wall representation in 5D? Remember, the way we did the Wall representation was that we took all the Dirac matrices and multiplied them together and constructed a gamma 5 operator. So suppose you try to construct an analog of the gamma 5 operator in 5D. Well, what would you do? You would multiply all the Dirac matrices, and now gamma 5 itself would be involved in that. And the question then you would ask is that, is this new gamma 5? How does it, what is it? Does it commute or anti-commute with all the gammas? You can show by explicit computation, if you like, this new gamma 5 actually commutes with all the gamma mu's. Not just that, you can show that this new gamma 5 is actually just the identity matrix, or proportional to the identity matrix. Which means that you cannot use Schur's, what does Schur's lemma tell us? Well, it's not a proof, but you can find that there is no other matrix which commutes. You can basically show that the matrix that commutes with all the matrices of the Dirac representation in 5D is just the identity matrix. And therefore, in 5D, the Dirac representation is not reducible. Okay? So this turns out, so this is happens in every odd dimension. So this phenomena, so in every even dimension, we can define Weyl fermions, but in odd dimensions, we cannot define Weyl fermions. Okay? If you want to read about the property of different kinds of representation of the Dirac algebra in all dimensions, starting from 2 up to 12, then I recommend the Polchinski's String Theory book, Volume 2, Appendix, the first appendix. The appendix has an exhaustive discussion on the algebra of the representation of Dirac algebra in every dimension, up to 12. In the 12, he uses 2 time dimensions because he wants to get to F theory. All right, Laura, I am going to switch to the presentation now, so maybe the lights can be a bit dimmed. Thank you. So today we are going to discuss the Feynman rules for fermions, but in the context of Yukawa theory. And after that's done, we are going to start on, electromagnetism. So this is, let me remind you, the Lagrangian of Yukawa theory. Are the fonts big enough, or do you want me to make it a bit bigger? Okay? Is that good? Yeah. All right. So, so the nuclear Lagrangian that we were looking at is has a free Dirac, has a Dirac part. It's a Dirac Lagrangian, and that describes the nucleon and the antinucleon. And there's a meson, and this is a real scalar field with a big mass, and this is the Yukawa interaction. And we want to compute this thing. We want to compute what the transfer matrix is between an incoming state, which has some momentum K1 and K2 and spin label R1 and R2, and this outgoing state. And the LSZ reduction formula tells us that to do this, we have to look at this object. And so here is a Dyson, there is a time order exponential. And this object is given in the interaction picture. I hope Dan went into the details of these things. And so then we talked about, well, we have to use Wick's theorem to expand the time order exponential. So we talked about, we proved in class part of Wick's theorem for 2 fermions. And here's Wick's theorem for 2 fermions. This is a contraction defined in this way when we have psi and psi bar. If the contraction between 2 psis and 2 psi bars are defined in this way, and then you can compute that to be 0. And here's the outline of the proof, and it's been uploaded in the wiki. So now we can extend Wick's theorem to multifermion fields. So if you have multifermion fields, suppose we have a time order exponential of a bunch of fermion fields, then Wick's theorem can be shown that it's the normal ordering of all those Fermi fields, and then all possible contractions times the remaining fields have to be in the normal ordering. So to figure out how do you get all possible contraction, let us look at a case where we have, say, 3 Fermi fields, and you're going to contract between 2 Fermi fields which are not adjacent to each other. Okay? So the way you do this is that you anti-commute. So to contract psi 1 and psi 3, you anti-commute psi 3 through all the Fermi fields which are in the way. If there are bosonic fields in the way, you have to commute with those. And then you bring them next to each other. And once you brought them next to each other, you say, aha, but this is no longer an operator. This is just some propagator, some function, some C number function. So I can now pull it outside the normal ordering. Okay, so this is how, if you have more than one Fermi fields, this is how you figure out how to use Wick's theorem. Yeah?
But you do this until you don't have anything inside the normal ordering, or you
no?
You have any field?
Yeah, I mean you can actually have. What does Wick's theorem say? You like the first term here would be only 1 contractions times normal ordering of all the different fields. The second term would be 2 contractions, all 2 possible, and all the remaining fields, until you go down to the lowest number possible. It could be there's no contraction left if the original number of fields were consistent with that, or they could have one normal ordered field left, right? So we will see example of that very shortly. By the way, those of you who came a bit late, this is the reference for spinors in arbitrary dimensions. And this is the solution to the puzzle of gamma 5 in 5 dimensions. But you can come and talk to me afterwards if you are. So let's just remind ourselves what the field operators look like. So we are in the interaction picture. So effectively, we are just doing everything in terms of free fields and free, the free vacuum. So this is our Dirac field. It has an annihilation for the particle, a creation operator for the antiparticle. Psi bar has a creation operator for the nucleon and destruction operator for the antinucleon. And the meson is a real scalar field, so it has an annihilation operator and a creation operator, and these are Hermitian conjugate of each other, so that this is real. Our in state is a two-particle state. Let's start with that. So we are interested in nucleon-nucleon scattering. So we have to create two nucleons, and the way to create them is by using the B dagger operator on the vacuum. And our final state is also a two nucleon, so we create them in exactly the same way. And then we take the Hermitian conjugate of this, and then therefore the daggers become the creation operator become replaced by annihilation operator. So this is a cartoon of what is happening. Sorry?
You just go back.
Yeah. Oh, I'm sorry. Yeah. Okay.
Yep.
All right. Sorry, I'm a bit fast when it comes to slides. So this is the cartoon of what's happening. For me, time always flows sidewise, okay? I'm one of those guys. It doesn't go upwards. For some people, it goes downwards. So here is the nucleon, the two nucleons coming in with momentum, and then the two nucleons going out. This is not a Feynman diagram. It doesn't have all the features that we would like to have on a Feynman diagram, okay? And our interaction Hamiltonian is this guy. Has a psi bar, psi, phi on it, and there's a lambda. So let's denote the part of phi which creates the annihilation operator by phi plus. This is not phi dagger. And the part of phi which contains the creation operator phi minus. Now see, neither our in state nor our out state has any phi particles, right? So the annihilation operator will just commute with all the stuff, the B dagger operators which created that in state. And therefore, phi plus will annihilate the in state. Is that clear? So basically, the in state is something where we have two B daggers acting on the free vacuum. So if I apply on it phi plus, which has in it the annihilation operator of the meson, then if I apply phi plus on the in state, I'm effectively computing this thing, A, two B daggers acting on 0. But this and this will commute because this is a bosonic operator and this is a fermionic operator. So it commutes with this, and then it kills the vacuum. Therefore, we get that phi plus acting on the in state is 0. Similarly, phi minus acting on the final state or out state will give you 0.
Sorry, Tibra.
Yeah?
What will happen again if the in state was a meson?
Then that would not be 0, because then you would have, say, if the in state has a meson, then you have A and acting on it, but then there would be an A dagger somewhere, right? So they will commute and give you a delta function with and a delta, so that would give you some non-trivial contribution. Okay, so you would get some delta function with the momentum and stuff on the right. Okay? Very good. So this implies that O lambda, the order of lambda contribution, is 0. Why is that? Because here's the time ordering, and then this guy does not contract with anything, right? This guy is just hanging out by itself, sad. And sad people are not to be trusted. They kill the in and out state. Okay? However, the second order contribution would be non-zero. Because there would be a term in the Wick's expansion where you would have a contraction, and that guy will not eliminate either the in state or the out state. And that is a term that we're interested in. Because everything else, any term which doesn't have this contraction, will not contribute. So we look at that term, the term where there is only one contraction. You might say, what about terms where our contraction between these guys? You can show that those terms will be 0. And that's because you have 2 particles in the in state and 2 antiparticles in the out state. And so the number of operators here, basically, you can think of it as the 2 particles which are coming in have to be kind of somehow absorbed, and then the outgoing particles have to be created. So the number of operators in there has to be equal to those number of particles in the external state. Otherwise, you get 0. That's not obvious, so it's kind of, you have to actually work that out. At least it's not obvious to me right now. Maybe there is another way of looking at it. Okay, so now what I've done is that right. So now these guys, psi and psi bar, have B daggers, B, C daggers, and C in them, right? Again, by the same argument as before, we are only interested in the parts which have B and B daggers, because our outgoing particles and incoming particles don't have antiparticles. So the antiparticle operator will either annihilate the incoming state or the outgoing state. Okay? This is analogous to this argument. So that means that so here I am denoting by psi 1 the operators which are in space-time point x1, and psi 2 by operators which are in space-time point x2. So here what I've done is that I have expanded out these guys. I have kept the bars, then I've expanded the psi 1 and psi 2 out, and I've only kept the B part of them. The C dagger part of them I have discarded because those will annihilate. And I have normal ordered them, and this is basically what happens if I normal order them. I pick up a minus sign because there was a B dagger here. I have brought it over here. Here it is. So that means that I had to anti-commute this with this guy, and there's a minus sign that I picked up. And I have written out the in state explicitly. And the psi bar 1 and psi bar 2 are they are contracted with the spinor part that was in psi 1, which is over here, u of t of k1. Psi bar 2 is contracted with the spinor part over here. Okay? And these exponentials come from expanding the Fourier modes of this guy and this guy. So now we have 4 B operators, and then you can basically apply the anti-commutation relationships. And you can just apply them until all the B's go to the right and annihilate this guy. This term that survives has this form. It has 2 terms with delta functions in them. So now what we can do is that we can use these delta functions to do the K1 and the K2 integrals here. And we can use the Kronecker deltas to do the sums, spin sums T and T prime. There's too much to write here, but it's you have all the notes, right? So if you do this, then what happens is that you get 2 terms, of course, because we had 2 terms here. And in the first term, see the delta function? K1 is set to K. So there was K1 here, that's set to K. K2 is set to P. There was K2 here, and that's set to P. Similarly, in the exponentials, K1 has been set to K, P1 has been set to P. And in the second term, K1 has been set to P, and K2 to K. Okay? And then the T has been set to S, T prime has been set to R, and similarly on the second one. So then we can do an expansion. By the way, this is roughly based on computation done in David Tong's lecture notes. So you can also refer to that if you want. So now we can expand the psi bars and then do a similar computation. And then for the first term here, we find this as the result. So I'm not coding the whole result. I'm just coding here the first term. And here you see, but here what we have done is that we've expanded out the out state. And then so you have to apply the creation operator on this guy. So you're not messing with this anymore. And this is the result you get. And then here you get a vacuum. Having done all the anti-commutation algebra, you have used up, there is no operator left. So the vacuum and its Hermitian conjugate friend, they are happily reunited, and that'll give you 1. And I have written the contraction of the phi field as the bosonic scalar from Feynman operator. You see here the U, but they will contract with the spinor coming from here. This U will contract the spinor coming from here, and that's what happened here. And delta functions will there'll be 2 more exponentials coming in. Okay. And there is a minus sign relative in these 2 terms. So next what we can do, we can now expand this, the Feynman propagator for the scalar. And it has this form, right? So, but there's probably a minus I here. So there might be a typo there. Sorry about that. Or maybe not. So then what we can do is that we can, okay, write this, and now we can do the dx1 and dx2 integral. And what does that do for us? See here, there's an exponential and x and y in it. And the exponentials here have, yeah, so I've written it x and y, but they should be like x1 and x2, right? So this should be x1 and this should be x2. And there's x1 and x2 here, x1 and x2. So you get 3 exponentials with x1 and 3 exponentials with x2 when you expand this guy out. And then when you do this integral, you should get a delta function with 3 arguments, momentum arguments, right? And then in the second term, you get another delta function. Sorry, yeah, you get 2 delta functions with 3 arguments. When you do the x1 integral, you get a delta function which involves p prime, k minus k plus q. This is this delta function. When you do the d4x2 integral, you get a delta function with k prime minus p minus q. And that is this delta function. You do the same thing in the second term, and you get these 2 delta functions. But you still have a q integral left. And if you do that, then these 2 delta functions and these 2 delta functions will combine. And then you get this. The one thing I forgot to mention, and I skipped over, is the fact that this was supposed to be the computation for just this one term. And but if you now do the computation for the second term, you see that it gives you exactly the same result. So the fact that there was like a factor of half here, that goes away because you add these 2 results. And that's why in this final expression, you don't have a factor of half. So here I'm saying by relabeling, you can show that both terms in IT are the same. And so basically, this is the result you get. So you get 2 pi to the power 4, an overall 4 momentum conserving delta function. You're doing a second order diagram expansion. So you had a minus I lambda squared coming from there. And then you have this complicated stuff. So if I were to, or you were to do all these steps, whenever you wanted to compute like the scattering cross-section of some scattering process, you would die of boredom, right? And you can see that there's nothing very fancy or complicated or deep about this computation, right? It's really mechanical. So you should be able to automate this process, and that's what the Feynman rules allow us to do. So let's look at this expression and represent it as a diagram. And this is my diagram. I'm going to draw the diagrams on the, because on the sideboard there. So for the fermion, I've used a solid line. over there for the meson, I've used an orange line, which here I'm using dash. So you have a fermion with momentum P and spin label R coming in, another fermion with momentum K and spin label R coming out, and then the two fermions which are coming out have momentum K prime and S prime. I did not put the prime on that S there. Sorry about that. And then there's P prime, R prime. And this is like none of these are S channel diagrams. They're T or U. So we figured, some of you figured out in the tutorial that when the external particles are not charged, you cannot have both S, T, U, all three channels. When the particles are charged, you cannot have all S, T, U, right? And the other diagram is second one. So I like to keep my incoming momentum and outgoing momentum in the same place. The way I think about it is that there is some source here which is shooting out this particle, and there's some source here which is shooting out this particle, and there's some detector here which is receiving this particle. Although this is all in momentum space, and there's a different receiver here which is receiving this particle. So to do this, the other diagram I'm going to write is there's a momentum coming in. See over here, the particle with momentum P came in here, and then over here there was a particle momentum K prime was emitted. But that particle could have come from here. So the other is K prime of S prime. And this particle could have come from this vertex. And you might say, why are there so many arrows here? We are coming to that as well. And here we have internal momentum is P minus P prime. Okay. So I'm just reproducing these two diagrams. And I'm claiming that these diagrams correspond to this matrix element. And the way to do this is, I'm going to come back to this, is to adopt these rules. The rule is that for each incoming fermion of momentum P and spin polarization R, we associate a UP with label R, sorry, UPR, and draw the following diagram. So for this thing, I draw, let me come here, U P of R. For each outgoing fermion, we draw particle like that. For this kind of diagram, we write U bar of PR. Sorry, there should be an R here. And over here, the outgoing particle is, so the particle came in, and this particle came out. So there should be a U bar for this guy, right? According to, so let me write the U bar. Where do I write this? This is a column matrix. If I write it on the right-hand side, I would get a 4x4 matrix. I'm actually trying to get a scalar quantity. So I write it on the left. So you are prime of P prime. So it would have made sense if I took one of these fermion lines, and there's an arrow on the fermion line, and the arrow means that the particle, which I'm describing by this line, is charged. See, there is no arrow on the line, the meson line. These arrows are the flow of momentum. These arrows are the flow of charge. So I could have saved myself a trouble if I said, okay, for every fermion line, I'm going to go against the arrow. And if I'm going against the arrow, here I'm seeing it's an outgoing particle. Whenever we have an outgoing particle, and in the English language, we write from left to right. So if we were doing this in Arabic or Hebrew, we should probably go right along the fermion line. But in English, it's better if you go against the arrow and you're writing left to right. Okay? So let's see what happens for this guy. So here we should have a U bar S prime K prime, and then here there's an incoming fermion, so there should be U R of K. Do you guys agree? Okay, good. What else do we need? So yeah, my number 3 is that we label the fermion lines with an arrow so that the arrow flows in the direction of time. So time is going from left to right. Yeah. If we will see for antifermion, it goes against the flow of time. We write down the spinor factors from left to right as we follow the fermion line opposite to the direction of the arrow. It doesn't matter which fermion you start with. Here we see that I started with this guy, this fermion line, but I could have started with this fermion line, and that's because this object is now a scalar. This object is also a scalar, so they commute. They are not matrices. Okay, what other things do we have? So we don't have antifermions in this case. So but for antifermions, you will have, for an incoming antifermion, you write down V bar of R. For an outgoing antifermion, you write down V of R. Again, you write it from left. Do you have a question, Ahmed? Okay. So again, you write down from left to right while you follow the fermion charge arrow go against the charge arrow. And the next Feynman rule is that associate with each vertex a factor of I lambda. So these two Feynman rules are not relevant for these diagrams because we don't have any antifermion here. But the next one is, so for each vertex we write I lambda. So we have minus I lambda squared. Yeah?
Go back to the Feynman diagrams for the nucleon scattering amount.
Like the original ones?
No.
These ones?
Keep going down. Straight out of contact. It says figure 7.
Oh, I'm sorry.
So the next figure, I think.
Yeah, this one.
Yeah, are you saying...
That's a different process, by the way.
Okay.
Yeah.
That's like antinuclear.
Yeah, that's antinuclear. I haven't come to that yet, sorry. Yeah. It's just, I'm actually using the lecture notes as slides, which one shouldn't do, but there are only so many hours in the day.
Yeah.
I couldn't make lecture notes. Maybe next year's class will get lecture notes, slides. So sorry about that. So, okay, so So we have, so these are the minus I lambda vertex that you associate with all of these guys, where time is going right. Right? Is there anything I've forgotten? Yeah, you could just switch this with this, right? So the arrow could be coming like this, going out like that. And here the arrow could be going like that, coming out like that. Okay? So with all of these things, you associate minus I lambda. But for our purposes, it's really these guys which we are using. Okay? We haven't used these ones for this diagram. Okay, what other? Okay, let's see. Okay, so I'm not following it chronologically. I will come back to that, but that's because all right. Let me go back to this thing. All right. The other thing that we need is something that you learned already in your scalar field theory course, is when you have an internal propagator, which is a scalar particle, a spin zero particle, you need to include its propagator, right? So the propagator for a scalar particle, remember, is I p squared minus m squared. So over here, the momentum of the internal particle, there's a factor of I somewhere. Let's put this over here. And there's an internal particle that's p minus p prime squared minus m squared. And there's a I epsilon as well. And that is precisely what we have derived here, except this minus sign. So if we use the same Feynman rules, we would actually get exactly this guy. But this minus sign is a bit tricky. And we will actually explore it thoroughly in tomorrow's tutorial. So tomorrow's tutorial will be essentially dedicated to minus signs in Feynman diagrams involving fermions. But but let me mention, do that argument here as well. Okay, so we saw this. So I told you about the Feynman rules for the antifermions, but to actually derive them, you basically have to do an antinucleon scattering. This should be antinucleon. Thank you, sorry. So you have, time is flowing this way. There are two antinucleons coming in. So if you do exactly the same kind of calculation, but instead of B's, you will have C's, you will get these Feynman rules that for all incoming antifermion, you have V bar, and outgoing antifermion, you have V of V, and the same rules as here. And then right. So label antifermion lines with arrows which flow opposite the arrow of type. This arrow represents the flow of charge. Again, write down the spinor factors from left to right as you follow the line against the arrow. Same rule as before. So to derive the Feynman rule for an internal fermion, there is no internal fermion in this case. We have to work out the process that involves a nucleon-meson scattering. So a nucleon coming in, scattering with a meson, and going out. And if you do that, you find that this is your internal propagator for the fermion. And the internal line is written by, is just, this is just represented like that. So remember, there was a delta function. So we impose 4 momentum conservation at every vertex. So at every vertex, you have to make sure you have 4 momentum conservation. And that's why the momentum going through here was p minus p prime. We could have easily written the momentum going up in this way as k minus k prime. Similarly, over here, we could have, instead of this arrow, we could have done this, where this is the momentum going up is k minus p prime. Okay. Now we come to a discussion of the minus signs in fermion. So for fermionic final states with indistinguishable particles, so that is our case, we introduce a relative minus sign if a diagram can be converted into another diagram by an odd number of permutations of the momenta and spin labels of the fermions. So this is just a formal thing. Is that if you take this diagram and we could convert this diagram to this diagram by relabeling the final states, then there would be a minus sign. And indeed we can. Suppose this is not, this was k prime and this was s prime and this was p prime, this was r prime, then basically it's topologically equivalent to that diagram. Right? So in that case, there would be a relative minus sign. I think it's better to find out the sign in a different way, and after a while you actually get a feeling for it, where there should be a sign, where it shouldn't be. So when the final particles are distinguishable, say a fermion antifermion final state, you can still have a minus sign. And this minus sign comes about how the operators in the normal order term of the Dyson series expansion interacts with the external state. And what do I mean by that? Suppose you take the case of a nucleon-antinucleon scattering. So these are the two diagrams possible. So see, you have a nucleon coming in, and it's annihilated here, and then another nucleon going out. Antinucleon coming in, absorbed there, and another antinucleon going out. So if you look at the Dyson series, the formula expansion, and the second order diagram, which kind of is responsible for this diagram, is this guy. So here I have put the creation and the annihilation operator indices labels to denote which part of psi bar and psi are responsible for this diagram. So there are these particles coming, particle-antiparticle coming in, and what happens is that these two things are at different space-time points, and they are the ones absorbing the particle and the antiparticle, right? So you can think of this guy has like a annihilation operator for the particle, and this guy has the annihilation operator for the antiparticle. Whereas these two things, they have the creation operator for an antiparticle and the creation operator for a particle going out. But to get from this arrangement to this arrangement, you have picked up a minus sign. If I now look at this second diagram, you see that the particle-antiparticle are absorbed in the same place, and that means that the labels here both have to be the same, and the particle-antiparticle are going out from the same point. This means the label here has to be the same. So, and you get this from this arrangement of the operator in the Dyson series expansion. And this thing and this thing do not have, they have a relative minus sign. And that's where basically this minus sign comes from. This is kind of to give you a flavor. Tomorrow's tutorial will explore it in more detail. And this actually is, yeah, you actually have to do a few more examples, and we'll do those examples tomorrow, okay? So there are higher order diagrams where there's an internal loop. And whenever there's an internal loop, the momentum there is not determined, fully determined. So for example, there, if we go to fourth order, so this diagram could have, is going to be modified by this. So here we have two fermion propagators. So the momentum coming in here was, say, P minus K prime. Let's call that, say, S. Or not, S is not a good idea. Q, okay. So the thing is that, so there's Q momentum coming in. So if Q plus T momentum goes this way, minus T momentum must go this way, right? So that on this point, momentum is conserved, and it is Q. However, we don't know what T is. It is not fixed by the external momentum. When this happens, we actually have to integrate over this internal momentum. And not only that, we actually, there will be two propagators here. There's a one Fermi propagator coming from here to here. And let's write that as Q plus T // minus M. And then here's another propagator coming from here to here. And that's going to be I minus T / minus M. Now, you might say that is not the fermion internal propagator I mentioned. I had something else here. But what this thing is that you can rewrite I P / minus M by P squared minus M squared. You can factor, there should be a plus sign, right? Okay, yeah. You can factor this as P / minus M, P / plus M, and then cancel these things out. I think there's a plus M, but let me confirm that later. So so this becomes our fermion propagator, okay? So okay, that's why I've written these fermion propagators. And so this is just, you know, this is a 4x4 matrix, right? It has got spinor indices. This is a shorthand for this thing. And the Feynman rule tells you that whenever there's an internal loop, you actually have to trace over that internal the matrices of the. Sorry?
Is this incorrect?
No. I'm coming to that. So that you have to trace over those internal loops. And whenever there's an internal loop, fermion loop, there has to be a minus sign.
Of the propagator.
Yeah, I think I messed up there, right? It should be minus here. I think it should be minus here, so that should be plus. So I think this is where I made the mistake, probably. What do you think? That should probably be a plus, right? Let me confirm that tomorrow, okay? Some of these rules we will explore tomorrow in the tutorial, the minus signs. For this course, I'm just telling you these things. We are not really going to go into loop effects. Okay? It's not very hard. It's just like time is short. So, you should do some computations yourself. Maybe you put one in the homework. Okay, anyway. So this is all I essentially have to say about Feynman rules. We'll get some practice tomorrow. Any questions? Yeah.
Could you go back a bit until we got the minus sign, the relative minus sign between two? Yeah, this one I think. Yeah. I mean, you told us that you have to put a minus sign if we can swap the final momentum and.
Yeah, in this case, this doesn't work.
Okay, so what is is there like a golden rule or is case by case? Because if you look at the diagram, it's a bit difficult if you don't go back to this machinery.
Right. So, right. So there is some. I mean, I remember reading somewhere, and also it's something that's borne out by my experience, is that whenever you have to switch two fermion lines, that's when you basically pick up a minus sign. So here you basically, if you want to go from this diagram to that diagram, you're somehow you're kind of. It's not very rigorous. You're switching two Fermi lines. In a sense, formal sense, you're also doing. Yeah, Aurora?
I was just gonna. So is it like when you're switching between like T and U channels, or?
That's what it appears. So I tend to be more careful about this. So I actually would prefer if you actually looked at the operators involved and figure out what the minus sign is. But right now, that's what's happening. Is that here you can actually get this diagram from this diagram by switching this guy. So taking this into the future and this into the past. And then, okay? So you're switching to, and this is probably somehow deeply related to crossing symmetry, but I don't have a clear statement on how this is related to crossing symmetry or things like that. So that's why, I'd rather have you guys think about it in this way. Sorry, you were saying something? Oh. Yeah.
We were just discussing which one got the positive sign, but I think we can.
Well, it doesn't matter.
You're going to square the matrix element. Anyway.
Yeah, what matters is the relative minus sign. Yeah. So, anything else? All right, so let's wrap up our discussion for Feynman rules and move to the next topic. Thank you, Laura. I won't need it anymore. So our next discussion topic is electromagnetism. So let's start with the most beautiful equations in all of physics. Faraday's law. This is Faraday's law. Ampere's law with Maxwell's correction. Gauss's law. And the statement that there are no magnetic monopoles. So these equations admit electromagnetic waves. They admit solutions which Maxwell showed was electromagnetic waves. I think it was the second Nobel Prize in physics. I think it was Hertz who showed that, who confirmed Maxwell's prediction and got the Nobel Prize for it. Back in those days, you could get Nobel Prize for pretty much anything. So this is famous for admitting electromagnetic solutions. It's also famous for being relativistic. These equations inspired Einstein to come up with a special theory of relativity. You all know the story. So we should actually write these equations in a covariant form. Now you saw in Neil's class that you can actually write these guys as a rank 2 antisymmetric tensor. They are, the electric field and the magnetic field are 3-dimensional vectors, but they are not vectors in 4 dimensions. And the first tutorial in special relativity was proving the fact that they're actually rank 2 antisymmetric tensor. Remember that tutorial? Relativity, first tutorial, parallel plates, you boosted in all different ways. I wrote that tutorial. So many years ago now. So we can rearrange these E's and B's in an antisymmetric rank 2 tensor. Because it's antisymmetric, the diagonal elements, well, first of all, I can write it as a matrix. And the diagonal elements are 0. So if you're wondering where so something's wrong. There should be a minus sign here. These signs come from, it comes from this definition. The 0I component is given by this, whereas the ij components given by these. We also need to write them in a relativistic form. We also need to express the source as a 4 vector, so that these are the 3 components of the current, and this is the charge density is the 0th part, so these are current densities. Then Maxwell's equations become 2 relativistic equations. First one is the divergence, the 4 divergence of x of f is 0, not 0, sorry, is j nu. And the second equation is this. Since f is antisymmetric in mu and nu, this equation can be rewritten using that fact. You can rewrite it like this, and that's often how this is presented. These are Maxwell's equations. Now, see this, if I compute this, this is antisymmetric in mu and nu, and this is symmetric. Therefore, this thing is identically 0. So applying this to this equation, this means that the current better be conserved. There's an alternative formulation of Maxwell's equation, and that involves introducing a gauge potential. I will come to what gauge means eventually. It's a historical accident. So it's a 4-vector potential, customarily written, represented by A. And it's defined in a rather strange way. It's defined in such a way that its derivative, antisymmetric derivative, gives you the field tensor. So I'm going to drop the x dependence. Annoying to write it. Okay, so this is how this is defined. So if you do this, then the first of Maxwell's equation becomes the D'Alembert operator acting on so the D'Alembert operator is the Minkowski space general, is a wave operator in Minkowski space. So this is a so this is what our first Maxwell's equation becomes. The second Maxwell equation is this. Because F is already antisymmetrized in mu and nu. But this equation doesn't have any new content. Why? Can someone tell me? Why is this equation isn't automatically satisfied in terms of A? I know you know the answer. Anybody else? So partial derivatives commute. So you're anti-symmetrizing partial derivatives, right? So remember, if you had some two objects which commute, say, right? These guys commute, right? So if you anti-symmetrize them, you get 0. So that's why this thing is, sorry, what am I saying? Yeah, that's yeah, that was right. Yeah. Okay. So expressed in terms of the gauge potential, it's really only this equation which has any dynamical content. The other equation becomes just a just an identity. So you might say, why do we need the gauge potential? People usually talk about how it makes life easier in quantum mechanics. In quantum mechanics, there are effects such as Bohm-Aronoff effects, which we want to, it's only, you can only understand them if you think in terms of gauge potential. We'll get to that. But actually, I think it makes even near classical physics nicer. So remember that, suppose you are studying the motion of a particle in a charged particle in an electric field, right? So the action for a charged particle in an electric field is something like this, where gamma is the path that the charged particle takes. So this is gamma. If it has mass m, d tau, tau is some parameter which describes where in this trajectory that particle is. And then the coupling between the electric field and the particle is given by the particle's charge. Let's call it E. Probably Q is more conventional. And then the vector potential times the coordinate of the whirl line of the particle. Okay? So using vector potential, it's a very natural and easy way of studying the dynamics of particles moving in a charged field, for example. Now let me draw an analogy with GR. So in GR, you know that if you want to study, say, how a particle is moving in some gravitational field, you have to use the geodesic equation, right? Or so the geodesic equation involves the Christoffel symbols. They're called symbols because they are not tensors. Okay? So in a sense, the Christoffel symbols are not the thing that you really observe. So in electromagnetism, the things that you really observe are the electric field and the magnetic fields, right? But for mathematical convenience, it's the A mu make life much easier to deal with the mathematics. This is analogous to using the Christoffel symbols to describe the motion of particles in a gravitational field. my memory is a bit rusty, but is this something like this that you look at when you're doing GR, right? Right, so you do something like this, right? And then, right?
Equals 0?
Yeah, equals to 0, right? So that's the geodesic equation, right? So in GR, you have something called a covariant derivative. And if you have some vector, some physical vector field, then the covariant derivative gives you the curvature, the Riemann curvature, right? And it's really the Riemann curvature which in GR is the physically observable thing. But the interpretation of this equation is that you go around some small loop and you measure the curvature which is contained within that loop. Analogously, we will see that when you're considering, say, a Fermi field, which in the presence of an electromagnetic field, you can introduce an analogous covariant derivative for the Fermi field. This is the charge of, well, classically it's a strength of coupling between the Fermi field and the electromagnetic field. And then, if you take the commutator of this covariant derivative acting on this Fermi field, or it doesn't have to be a Fermi field, it could be a wave function, then you get the electromagnetic field strength. So this equation is exactly analogous to this equation. And the equation of motion that you get from there is just analogous to this equation. Okay? So in some sense, you have something called a potential, and you have something called a field strength. It is also known as curvature in both cases. And in GR, the potentials are given by the Christoffel symbols, gamma, mu, rho, sigma. And in electromagnetism, they're given by A mu. In GR, the field strength of the curvature is given by the Riemann tensor. In electromagnetism, it's given by F mu nu, the field strength. So potential. So this is like a perfect analogy. These are actually mathematically, the relationship between this and this and this and this, it's the same relationship. So even in classical physics, we use potential all the time, right? When you're using GR, you are actually, always a lot of times you're just using this. And of course, this has some reparameterization, nice reparameterization properties. Okay, so now quantum mechanically, the gauge potentials are extremely advantageous. So in quantum mechanics, A mu seem to be needed for quantization. of the electromagnetic field, I have never seen a quantization of electromagnetism that doesn't use the AMU. Maybe it is possible, and maybe you can write a paper on that. So there are global effects in quantum mechanics. In quantum theory. Which require the presence of AMU. And the Bohm-Aharonov effect is probably the most famous of these. And I think it was Aharonov's PhD work with Bohm. Aharonov is still around. He comes here and says controversial things about quantum mechanics, which we love. So suppose you have some source of electrons, and you have some screen with two slits in them. Sorry, a barrier and a screen over there. And just behind the barrier, you have a solenoid. So this is a solenoid. And there is some current going through the solenoid. So there is a magnetic field. And here I've drawn the magnetic field as going into the board. But you can show that the magnetic field, even though it's zero inside, it's non-zero inside, it's zero outside. If you take the solenoid to be long enough in the part of the, so it's jutting out into the board, from the board, the part of the experiment where the electrons are actually non-zero probability of being, there is no magnetic field outside the solenoid. However, mathematically, the gauge potential is A0 outside. And if you want more details on this, I recommend Ryder, quantum field theory book. That has a really nice discussion on this. It'll give you all the detail of what the form of AMU is and stuff like that. Okay, so the point is, the electrons are being shot out, and they're coming and impinging on the screen, and the probability of the electron interacting with the magnetic field is negligible. That's how you have set up the experiment. But if you change the current in the solenoid so that the flux in the magnetic flux changes, you can actually see a change in the electron interference pattern. So even though the electrons are not directly interacting with the magnetic field, because they know that the AMU in the region of space where, so B is 0 here, but AMU is not 0, because they're interacting with AMU, they know that the flux here is changed. Okay? You guys, is this like something amazing? It's actually kind of not, from a certain point of view, right? Suppose again, I go to GR. Suppose you have some flat space, and there's a cosmic string here. But you didn't know there was a cosmic string here. According to GR, it would create a conical singularity. Okay? And you had some experiment, some spaceship with some very delicate instrument, some gyroscope or something like that, and you went around this cosmic string. And you did what is known as a parallel propagation experiment. So you're looking at whether a vector is changing, as you move along some trajectory, whether or not the vector is actually parallel to each other. So right? So you're always carrying it parallel. But you come back to the same point, and because these are identified, you see that if the initial vector was like this, the propagated vector is actually rotated. So another way of drawing this is that this space is locally flat, but there is a conical singularity here, and you have gone around this cone. And you'd find that a vector field will be parallelly, it'll actually, if you parallel propagate a vector field around that, it'll have a rotation. This is known as the holonomy. Here, what is happening is analogous to that, where the electron is kind of, sensing something, some hole in space, so to speak, hole in the space that it lives in. Whereas this is a quantum mechanical effect, this is a classical effect, but the mathematics are very analogous to each other. Okay, so let's stop here, and I will continue next time. I apologize for the handwritten notes, but I just don't have enough hours in the day anymore to give you typed up notes. But if you have any problem with the handwritten notes, please come and let me know, okay?